Hello everyone, and welcome to this quick Godot tutorial on how to create a moving platform in a Godot 4 C# game project. By the end of this video, you'll know how to use a path and a path follow node to have a platform move along a specific curve, how to have this platform loop or walk back the other way, and finally how to ensure that the collider of the platform follows the visuals properly so that a character can actually walk on it. Note that in this tutorial we'll see an example in 3D, but everything works just the same with the 2D version of the nodes that we'll study. And of course, as usual, don't forget that if you want to get the files of the tutorial directly, you can have a look at the GitHub repo with all my Godot tutorials over here. Also, since we'll be coding our logic in C#, make sure that you're using a version of Godot with .NET enabled. Oh, and by the way, if you're still a bit new to Godot 4 and C# game dev, you might want to check out my brand new short-read ebook, L'Almanach Getting Started. This quick practical guide will have you explore the fundamentals, and it will teach you how to set up scenes, program in C#, design UIs, and even build your own tic-tac-toe game step by step. So if you want a way to embark on your Godot 4 C# journey in less than 100 pages, and for a low price, don't hesitate to have a look at the Gumroad page over here. But anyway, with all that said, let's dive in and discover how to set up a moving platform in Godot 4 and C#. Alright, so first of all, let's see how we can move our platform easily along a path. In Godot there's actually a couple of node types that are extremely useful when dealing with this kind of use case, the path and path follow nodes. We talked about those in this previous tutorial of the series, on a 2D example, when we talked about spawning enemy waves regularly and moving them along a predetermined path. Today we're going to see how to do something similar in 3D, and with a bit more customization of the object's movement. Oh, and also, I'll be using assets from Kenny's amazing free library, and more specifically, his brand new mini dungeon kit. Now, I've already prepared the platform object that we'll be using today. You can find it in the GitHub if you want, or recreate it from scratch. Basically, it's just a physics body with a collision shape and a few meshes for the visuals, but be careful because the body type isn't a static body. Because even if we're doing an environment object, which we usually do with static bodies in Godot, we want it to move in our level and still collide with the rest of the objects in the scene that have physics enabled, typically our player avatar. So for this, the Godot team actually introduced a really cool new node type in Godot 4, the animatable body. So it exists in 2D and in 3D, and here we're using the 3D version. And basically it allows us to move our object in various ways, so from a script, using an animation player, or a twin object, or even a path, like we're going to do here. But no matter how you move it, by making sure that you've enabled the sync to physics option in your body's inspector, you basically tell Godot to synchronize the movement that was applied to the object with the rest of the scene physics. And so you still get collisions, triggers, and all that sort of stuff, but it's a bit less complex than a character body and a bit more powerful than a simple static body. But anyway, so since we already have this platform object that we can add to our main demo scene, the first step, as we discussed in the other video, is to draw the path we want our platform to follow inside a Path 3D node. Of course, since this time we're in 3D, we can place points in all three directions and create a non-flat path. Okay, now that we have our path, the next step is to just give it a path follow 3D child node and instantiate our platform inside. From that point on, if we play around with the progress or the progress ratio parameters of the path follow node, we see our platform moves along our curve. However, we should make sure to change the rotation mode of our path follow 3D node to none, because we don't want our platform to rotate as it moves along. And we're also going to toggle off the loop option because we want to better control the movement of our platform later on via our script. But now, of course, we also know that we can do all this progress update using code, So let's simply create a new C# script on our path follow 3D node called movingplatform.cs, and inside we'll only keep the process function for now, because that's where we'll modify our follow progress value to move the object along the path. Typically, if we define and export some speed value for platform, then we can use it in the process method to increase our progress value and translate the object until we've reached the end of the path, which we can check for easily with the normalized progress ratio. Also, don't forget to actually multiply the speed by the time delta parameter that we're given in our process function to make it more stable. And after rebuilding our project, we're now able to adjust the speed value in the inspector to our liking. Okay, at this point we have a nice moving platform that looks cool and moves along our path. However, there are two big problems. One, in this current implementation, the platform does the journey only once, and then it stops at the end, which is clearly not ideal for an adventure platformer game like our little demo. Now, of course, we could actually re-enable the loop option to have it start back from the beginning, but again, that's a bit too limiting, because what I actually want to do here is to make intermediate waypoints. The second problem is that there aren't actually any collisions on our platform. So if I were to add some player object to my scene and move it on my platform when it's close to the ledge, then you see I just fall through it. So now it's time to see how to solve both problems. First of all, we're gonna work on the one-shot movement issue and the waypoints mechanic that I just talked about. That's something that is actually quite a common thing in video games, because it makes it easier to hop on and off the platform during its course on the path. Second, when it reaches the end, the platform could either teleport back to the beginning instantly, like with the loop option enabled, or it could follow a curve the same way, but in the other direction. To do all of this, we're going to need to improve our C# script so that it understands the notion of waypoint and that it tracks its current moving direction. To begin with, however, we can simply define two new exported variables, pause time at waypoints and jump to start. The first variable is a float. It will be the duration in seconds that we want to wait at each waypoint, if any. So if it's 0, we'll get the same behavior as we currently have, meaning the platform ignores the intermediate waypoints, or else, if it's greater than 0, our platform will slow down for each intermediate waypoint, stop for a while, and then speed up again to reach the next one. The second variable is a boolean. If it's on, the platform will teleport back to the start point when it reaches the end of the path, and if it's false, it will backtrack to the beginning by moving along the path in the other direction. Okay, now that we have this in place, let's see how to add our waypoint by waypoint system. The idea here will be to store the positions of the different points on our curve and the current waypoint index to know what chunk of the path or platform is currently moving along. The trick will be to use the normalized positions of those intermediate spots. This way, we'll have values between 0 at the beginning of the path to 1 at the end of the path. Then, depending on the current waypoint index for platform, we'll know what segment to look at, and we'll be able to interpolate a float between the first from point and the second to point of this subpath, either linearly or with little speedups and slowdowns if we suppose to stop at each waypoint. So the really delicate part here is to properly determine the speed of a platform so that it's constant on the path. To avoid this issue, we just need to use some basic physics formula and actually base our interpolation on the expected travel time. As you probably know, the speed of an object can be computed by dividing the travel distance by the time it takes the object to travel said distance. But of course, we can also see it another way and deduce that traveling the distance d at the speed s takes a t amount of time. In our case, that's pretty neat, because we've already exposed our platform speed in the inspector, so that's user-defined data, and we can easily identify the distance that we want to travel between our from point and our to point based on our waypoint ratios and our total length curve. Meaning that we could easily set up a counter that counts down this time amount and then interpolate our platform's position along our middle sub-chunk to have it be at the first waypoint at the beginning of the countdown and at the second waypoint when the time has elapsed. Alright, so that's a lot of theory, and it's time to clear things out a bit by putting all of this in practice. So let's go back to our script and add a few extra variables to handle this waypoints mechanic. Here we need to keep track of the total length of the curve, the number of waypoints, the index of the current waypoint, and the list of waypoint ratios as a list of floats. Then in our ready function, we'll get our path curve data. This allows us to get the number of points in the curve, get the length of the curve, and go through each of the points in our curve to get the ratios. At the end of this initialization step, let's also make sure that we start our platform movement at the beginning of the curve by resetting the progress ratio and setting our waypoint index to 0. Now let's create a new private method called startMove. This will be the function that makes our platform move from one waypoint to the next one along our path. Now we're gonna implement and refine this method bit by bit, so for now we're gonna stay simple and just increment our waypoint index by 1. Then we're going to set up everything we need to handle the travel time counter and position interpolation that we talked about. All of this requires yet a few additional variables. First, the move from value, that is the ratio associated with the point at the last index. So that's the point that starts the sub-chunk of the curve we're interested in. Second, the move to value is the ratio associated with the point at the current index, which is the point that ends our current sub-chunk of the curve. Third, the move time, which, as we said, can be computed by taking the difference between our two ratios, multiplying by the total curve length, and dividing the result by our speed. Fourth, the move delay, which we will initialize to 0 and then increase in our process method until it reaches our move time value. So that will be our actual time counter. Finally, let's also set up a moving boolean to make it easier to know if we need to update our counter or not in the progress function. With all of this ready, it's time to replace our current logic with the interpolation system. So first of all, if we are not moving, we can just return early right there. Else, if we are moving, there are two possibilities. Either our delay is lower than the travel time, in which case we need to increase it by the frame time delta to update our time counter and move our platform. Or else we've reached our travel time threshold, and so we need to stop our movement, optionally stop at our waypoint, and continue our progression onto the next chunk of the curve. Now, to move our platform, we said that we want to interpolate its normalized position along our subpath. This is easy to do thanks to the matf.lerp method. This built-in function takes in the from and to values to interpolate between, and finally what we call the t value. This third parameter is the 0 to 1 value that determines how far along we are on our subpath. To start simple and make a linear movement, we can set this t-value to be move delay divided by the move time. Last but not least, when our counter is done, we need to make sure that our platform is exactly on the waypoint, turn our moving boolean back to false, and call a little function that directly restarts the movement to the next waypoint. Just before we do that, however, if our pause time at waypoints is not null, then we want to stop a bit because we've reached a waypoint, and so we want to actually use this pause time. To do this, we can create a mini one-shot timer with this value as timeout. If we make our reach waypoints function asynchronous and add the await keyword in front of our timer line, then we are telling Godot to wait for pause time at waypoints seconds before running the rest of our logic. While we're at it, we can also do the exact same thing at the very beginning in our ready function, so don't forget to make it async also, and so that's a way of telling the engine to wait at the very beginning before it starts to move. At this point, if we run our game, we'll get something that is quite similar to a previous trial, except that now we're actually taking into account all of our waypoints. So if we set our pause time to a higher value than 0, then we see our platform indeed stops for a little while at each waypoint. But of course, this brutal stop is not very natural. Ideally, we'd like for the platform to slow down as it reaches the waypoint. To make our movement smoother, we are going to boost our interpolation system with what we call a custom easing function. For now, because we are looping using our t-value as is, we have a linear movement. This means that our object has no accelerations or decelerations during its movement. It just starts and ends at the same average speed. To make a more natural movement, we just need to put this t-value inside a special computing function that transforms it into a more interesting curve, with some speedups and slowdowns. And luckily, there's this great website called easings.net that gives us the formulas of a wide variety of nice interpolation curves. In my case, for example, I'm gonna go for the quart ease-in-out easing function, and so I can find the formula on the website over here at the bottom of the page, and I can then re-implement it in C# like this. Finally, I just need to wrap my t-value in a call of my new easing function. And that's it! If we run our game, our platform now nicely slows down when it comes close to a waypoint, it stops for a while, and then it speeds up again on the next chunk of the path. Though we need to be careful because we only want to apply this special easing if we are actually stopping at the waypoint. All we have to do is use either our previous basic t-value if the pause time is null to get a linear movement, or compute our eased-out version if the pause time is greater than 0. And here we are! Our platform movement is now pretty cool, and it allows us to easily create optional stops and control the speed. But of course, when we reach the end of the path, our code starts to go on the fritz because it tries to find a point index outside of our ratios list. Basically, it's trying to move on a subchunk of the path that doesn't exist. So we need to handle the last phase of our movement, going back to the start point. So, as we said before, we want the designers to be able to choose between two different systems. Either a direct teleportation back to the start, or a round trip where the platform actually walks back the path the other way. The first case is easy to implement. We'll simply go back to our start move function, check for the current index, and if it's equal to a number of points, meaning that we've reached the last spot on our curve, we'll force our waypoint index back to 1. This way, we'll instantly be back to our first chunk of curve. The second case requires a bit more work. First of all, of course, we're going to need a new variable to know which direction our platform is going. By setting it to +1 for the forward direction and -1 for the backward direction, +1 being the default, we'll be able to use it in our start move logic as the index increment value and in the move from computation. This way, depending on its +1 or -1 value, we'll either get the point before or after our current one in the list, and thus our platform will move in one direction or the other. However, this also slightly complicates things for extra checks. Indeed, now we need to check both if our current index equals the number of points in the curve, or if it's equal to -1, because we could be reaching either endpoint on our path. So in our previous check, we'll start by using our jump to start flag to isolate our previous code. This way, if the boolean is true, we get the same behavior as before, and we just teleport back to the beginning. Now, if the flag is false, meaning that we want our platform to actually move back along the path to the start point, we'll change our direction variable to -1 and reduce our current index. Note that we need to reduce it by 2 and not just 1, because we actually did our 1 increment before our code realized that it should go the other way, so we have to take this extra offset into account. Similarly, for index which is -1, we needed to set the direction back to +1 and add 2 to our current point index. Okay, so that's pretty neat. We now have a complete moving scheme for a platform that handles various cycling options and is highly customizable from the editor with easy-to-use design tools. Now, to wrap up our tutorial, let's see how to fix our last issue, our intangible platform floor. Alright, so to really get a functioning platform system, one last problem we have to take care of is our player avatar just falling through if we try to walk on it. Now, as we said before, our platform is an animatable body 3D node, and our player is a character body 3D, just like we discussed in this previous episode of the series on making a 3D character controller, so it should work. In fact, what's truly happening here is that, although our platform is indeed being dragged along the path, thanks to the path follow node, its collider isn't. We can actually visualize this by going to our debug options and enabling the colliders debug. This is a known caveat of moving bodies using a path follow node, like we're doing here, but luckily there's an easy solution to our problem. We just need to use a remote transform 3D node. Now, in essence, this node is very simple. It allows you to synchronize the transform properties of a node with another. So you can push the location, rotation, and/or scale of the source onto the target node easily. To fix a collision, the trick is, rather than putting our platform as a child of the path follow node and move it directly like this, which doesn't properly update the position of the collider and invalidates our collision, to use a remote transform 3D node as a child of the path follow node, and then apply its location onto our platform that is somewhere else in the hierarchy. So, apart from updating our scene tree, we of course need to make sure that in the remote transform 3D nodes inspector we assign our platform as the target node with the remote path property. And in the update section, we can also toggle off the rotation and scale synchronization, since we're only interested in the location. And that's it! Our platform now moves exactly the same way as it did before, with all the same options, but if we try to walk on it, we see there's a collision and our player doesn't just fall through the floor anymore. So here you go! You now know how to set up a basic moving platform system in Godot 4 and C#. I hope you liked this tutorial and that it helped you understand concepts like interpolation, easings, or even Godot's paths and remote transforms. If you enjoyed the video, feel free to like it and subscribe to the channel to not miss the next ones. And of course, don't hesitate to drop a comment with ideas of Godot tricks that you'd like to learn. As always, thanks a lot for watching, and take care.